In this video, we're going to consider what happens when we have paired data that lies approximately along a straight line. So we're going to look at the linear regression model. And in particular, we're going to derive the equation of the least squares regression line. So this tends to deal with situations where data comes in pairs. So for instance, you can think of measuring individuals' weights and heights. And you could plot that as a scatter plot with weights perhaps plotted along the x-axis and heights along the y-axis. So you could measure a series of points, much like this. You could plot them, and very often in applications we find that they lie along a straight line, approximately. So the question then becomes, if we want to fit a line to these points, what's the best way of doing this? And the most common thing to do is to say, right, we want to place a line, a straight line, so that will have the equation of y is equal to the intercept plus beta naught plus the slope beta 1 times x. That's the equation of a straight line. We want to place that through the points in such a way that something is minimized, and what we typically minimize is the sum of squares of these yellow lines, okay, which are the vertical distances between the points and the line. So each of those yellow lines is called a residual, and so consequently the quantity that we try to minimize when we're trying to find this line of best fit, this least squares regression line, is the residual sum of squares. That's why it's called least squares. So what is the residual sum of squares? Well, it depends on the intercept beta naught and the slope beta 1 of our straight line. But in order to calculate it, what we do is we take the y-coordinate of each point. So that would be the y-coordinate of these blue points here. And for each of them, we subtract off the value of y that's on the straight line. So that would be subtracting off beta naught plus beta 1x. Okay, and that would be this point here. So this term in brackets under the sum is actually the length of your yellow line. And then you square that, you add that up for all of the points, and that's what the residual sum of squares is. And the line that we're going to think of as being the best fit for our points is actually the one that minimizes that residual sum of squares. In other words, it's the placement of the line that gives us the smallest residual sum of squares. Okay, let's see how we go about finding such a line. So first of all, let's remind ourselves of the linear regression model. So this explains how the y-coordinates and the x-coordinates of the points are assumed to be connected to each other. So we're saying here that the y-coordinates of the points are linearly related, so that's these first two terms, to the x-coordinates. So remember, beta naught is the intercept, beta 1 is the slope. These first two terms are the equations of a straight line. Now if we just have those first two terms, then all of our y-coordinates would be exactly along a straight line. And in reality, we know that that isn't very realistic for things like weights and heights or anything that's linearly related. So we've got to introduce some kind of random error. And we do this by adding on this EI term. And what we do is we say that these independent errors are normally distributed with a mean 0 and constant variance sigma squared. That's the typical model. Okay, how do we use this model? Well, we say that the expected value of y for a particular value of x, let's call it little x, is going to just be equal to the y-coordinate of the line at that point. So we're just taking expectations of this expression up the top here. What do we get? Well, we get beta naught plus beta 1x plus, okay, the expected value of EI is 0 because EIs are normally distributed with mean 0. Okay, now what I'm going to do is I'm going to just rewrite that slightly for algebraic niceness of what comes later. So I'm going to add something on and take it away, and that's going to be beta 1 x bar. I'm going to add it on, and then I'm going to subtract it. So I haven't really done anything here. Then what I'm going to do is I'm going to define a new variable. I'm going to call it mu. So mu is going to be equal to beta naught plus beta 1 x bar. There it is. And then what's left is, well, there's a common factor of beta 1 here, so what's left is beta 1 times x minus x bar. Okay, so all I'm doing there is just rewriting in terms of mu and beta 1 instead of beta naught and beta 1. I'm going to do a change of variables. And I'll say it again, the only reason I'm doing this so that the algebra in what follows is a little bit nicer. Okay, so here, yes, we've introduced this new variable mu. So we should rewrite the thing that we're trying to minimize in terms of our new variables mu and beta 1 instead of beta naught and beta 1. So in order to do that, here we go, the residual sum of squares, which depends on mu and beta 1. I'm literally just going to substitute in mu to replace beta naught. So this beta naught here becomes mu minus beta 1 x bar, and so consequently my expression becomes this white expression over here. So that's the residual sum of squares. How are we going to actually minimize it? Well, let's have a look. Residual sum of squares, we've written it now as a function of two variables, mu and beta 1. And if we want to minimize a function of two variables, this becomes a calculus problem. So I should take its partial derivative with respect to mu and put that equal to 0. Take its partial derivative with respect to beta 1 and put that equal to 0. So I'll end up with two partial derivatives that I want to calculate, set them equal to 0. That will allow me to find local minima, maxima, saddle points, these critical points that you'll have met in calculus. Okay, how do we do that? Well, let's first of all take the partial derivative with respect to mu of the residual sum of squares. Well, okay, underneath this sum we have a bracket squared, so by the chain rule, if we differentiate that partially with respect to mu, we'll end up with 2 times the bracket multiplied by minus 1 because of this minus sign in front of the mu. So what we end up with is minus the sum of 2 multiplied by this bracket. Okay, so that's simple enough. That's just using the chain rule. We can do the same for differentiation with respect to beta 1. This time we've got to be a bit careful, because rather than just having a minus sign multiplying beta 1, as we had the minus sign multiplying mu, we've also got this xi minus x bar multiplying beta 1. So when we differentiate this with the chain rule, we'll have minus the sum of 2 times the bracket multiplied by xi minus x bar. Again though, fundamentally it's just the chain rule. This is just partial differentiation. Now, these are the two partial derivatives. If we want to find minimizers, then we have to set them equal to 0. So for the points beta 1 and mu that minimize the residual sum of squares, and I'm going to denote those with hats over them, so we'll have beta 1 hat and mu hat being the specific points where the residual sum of squares is minimized, then at those points both of these partial derivatives will be equal to 0. So there we go, with the hats added on, we are trying to solve these equations here. Now, let's actually try doing exactly that. Here they are again. So I've labelled them equation 1 and equation 2 so that I can refer to them. So these just come about from writing the partial derivative of the residual sum of squares with respect to mu and beta 1 are both equal to 0 at the minimizer, so at mu hat and beta 1 hat. Okay, let's see what equation 1 gives us. Well, okay, we've got something equal to 0, so this factor of minus 2 that's around here, we can just get rid of. We can multiply by minus a half. And that will just give us this equation here. Now, if we split this into two sums and write this as the sum of the yi's minus the sum of the stuff in the curly brackets is equal to 0, and then add the sum of the stuff in the curly brackets to both sides, we'll end up with this equation here, that the sum of the yi's is equal to the sum of the mu hats from I is 1 to n plus beta 1 hat times the sum of xi minus x bar. Okay, how can we simplify that? Well, if we split this sum into 2, so we write this as the sum of the mu hats plus the sum of beta 1 hat xi minus x bar, then that first sum is just going to be n lots of mu hats, because mu hat isn't depending on I here. So we're just adding mu hat to itself n times. So n times mu hat is that first term. And then we'd have the sum of the rest of it, and the beta 1 hat we could take outside, because again it doesn't depend on I. So we'd have plus beta 1 hat times the sum of xi minus x bar. So, next question, what is the sum from I equals 1 to n of xi minus x bar? Well, in order to see that, maybe we should split that sum into 2, and that's what we've done down here. So I'm writing this as the sum of the xi's minus the sum of the x bars from I is 1 to n. Because x bar doesn't depend on I, then this is going to be n lots of x bar. But now if you think, well, what is the definition of x bar? X bar is just the sum of the xi's divided by n. So if we multiply that by n, we just have the sum of the xi's. So in fact, this curly bracket term here is nothing more than 0. So in fact, the sum from I is 1 to n of the yi's is equal to n times mu hat, which, okay, if we rearrange that to get mu hat on its own by dividing both sides through by n, we'll get that mu hat is equal to 1 over n times the sum of the yi's. And that's just the mean of the yi's. So in other words, we could write that mu hat is equal to y bar. That's what we found out. Okay, what about equation 2? Let's leave that on the screen and let's get equation 2 up. So again, there's this factor of minus 2 that I can immediately get rid of because I multiply both sides by minus a half, and 0 times minus a half on the right hand side will still give me 0. Then I can do exactly the same rearranging trick that I did with equation 1, and I can say, right, I've got the sum of yi times xi minus x bar being equal to the sum of the stuff in the curly brackets multiplied by xi minus x bar. And that's what I've done in this first line here. I've split it into 2 sums. I've rearranged it by moving the negative sum over to the right hand side. And then I can split this sum up. I can say, right, I've got the sum from I is 1 to n of mu hat multiplied by xi minus x bar. Well, the mu hat bit doesn't depend on I, so I can bring that outside the sum. So I have mu hat times the sum of xi minus x bar. Now remember, we just discussed what the sum of xi minus x bar was. It's 0. So in fact, this first term is going to disappear. And then what have I got left? I've got beta 1 hat times xi minus x bar times xi minus x bar. Okay, the beta 1 hat can come outside the sum, and then we've got the sum of xi minus x bar squared. Now, this is an important quantity. We call this a corrected sum of squares, and we've denoted this SXX. That's the common notation for this particular sum. And we said that this first term disappeared, so in fact all of this stuff on the right hand side here just comes down to beta 1 hat times SXX. What about this left hand side? Well, the quantity that in the lectures we refer to as SXY, which is defined as written here, with a little bit of multiplying out of brackets, we can say that that's the same as the sum of yi times xi minus x bar minus y bar times the sum of xi minus x bar. Again, we've got this sum appearing of xi minus x bar, and that's just a whole load of 0. So that term isn't really there. And what are we left with? Well, this term here is nothing more than what we've got on the left-hand side. So we've shown that this left-hand side is in fact the same thing as SXY. So we've got SXY equals beta 1 hat SXX. That's great. So that's what we just said. SXY is beta 1 hat SXX. We rearrange that to get beta 1 hat, and it's just that beta 1 hat is in fact equal to SXY over SXX. So now we found beta 1 hat, we found mu hat. Remember, our original task was to find the slope of the least squares regression line. We've done that, it's beta 1 hat. What about the intercept? Well, that was beta 0 hat, and remember we did that change of variables. So now in order to find what beta 0 hat is, we just have to transform everything back into the original variables. And if you look back at how we defined mu hat, then you'll see that beta 0 hat is therefore y bar minus SXY over SXX times x bar. Okay, so there we have it. We have found the least squares regression line equation by essentially just solving a minimization problem in calculus.